Engineers often chase raw flops, assuming more compute power equals better performance. This leads to unsustainable cloud bills and thermal throttling in production systems that cannot scale efficiently. The counterintuitive truth is found not in the world's largest data centers, but on a handheld gaming device, Valve's Steam Deck. By treating the APU as a constrained edge system rather than a raw compute brick, we discover how performance per watt becomes the ultimate metric for AI deployment. When you look at benchmark charts, they usually list theoretical peak floating point operations per second. These numbers suggest that if you want to run complex models or inference tasks faster, you simply need more power and bigger chips. This assumption is why many teams overspend on cloud instances only to find their systems throttling under sustained load. The heat generated by pushing silicon beyond its thermal design limits forces the system to slow down, killing performance just when it is needed most. Valve's Steam Deck challenges this entire paradigm. It proves that in edge inference, thermal constraints are often a harder bottleneck than raw flops. The hardware strategy behind the Steam Deck prioritizes sustained load within a small form factor over burst capabilities. The custom APU uses an AMD Zen 2 architecture designed to maintain high performance within a strict power envelope of roughly 15 to 30 watts. This is fundamentally different from standard desktop GPUs that are built for peak bursts but suffer when cooling cannot keep up with continuous inference workloads. When you run a large language model on a system not optimized for thermal efficiency, the chip hits its temperature ceiling and throttles rapidly. The result is inconsistent latency and poor throughput. Valve engineered their silicon to avoid this trap entirely by accepting lower theoretical peaks in exchange for consistent output over long periods without overheating. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. However, hardware alone does not tell the whole story of why this system excels at handling complex workloads efficiently. The real engineering magic lies in how they optimized the software stack to act as a force multiplier for that silicon. Valve did not just build a better box, they built a better ecosystem where every component works together to reduce overhead. This is visible in their open-source contributions, which serve as case studies for system-level optimization. Consider Proton, a compatibility layer with over 32,000 stars on GitHub. While often discussed in the context of gaming, it represents a profound engineering achievement in minimizing translation overhead between Windows APIs and Linux Vulkan graphics calls. For an AI practitioner, this means that tools written for one environment can run efficiently on another without the heavy penalty of emulation layers found in generic setups. The system translates instructions with such precision that the CPU does not waste cycles managing compatibility, leaving more resources available for actual computation. This is critical when deploying inference loops where every millisecond counts and resource contention must be minimized. Complementing this is GameScope, a custom session compositor designed specifically to manage frame pacing and resource allocation aggressively. With nearly 5,000 forks in the community repository, it demonstrates how Valve's approach to managing system processes differs from standard desktop window managers like X11 or default Wayland configurations. In an edge environment where memory bandwidth is scarce, this aggressive management ensures that inference tasks do not starve other essential system processes of CPU cycles. The result is a stable platform where the AI workload runs smoothly alongside necessary background services without fighting for dominance over shared resources. Further enhancing runtime efficiency is Fossilize, a serialization format Valve developed to handle persistent object types. By serializing these objects once and reusing them later, the system drastically reduces startup times and load overhead. In the context of AI inference, this translates directly to faster model loading speeds and smoother sustained throughput compared to standard desktop implementations that rely on generic resource management for every single request. When you are deploying models at scale, reducing the time spent loading assets or initializing parameters can significantly improve your overall operational efficiency. This technique mirrors the requirements for edge AI deployment where latency is a critical metric alongside power consumption. The dominance of C++ across their major repositories, including Source SDK and Fossilize, highlights a deliberate shift away from generic, run-it-anywhere bloat towards specific, run-it-here perfectly. This mirrors the exact requirement for production systems designed to handle continuous workloads in constrained environments. The lesson is clear. When deploying LLMs or complex inference models on edge devices, you must prioritize sustained power limits over burst ratings. A system optimized for 15 watts of sustained performance can outperform a machine designed for peak bursts if your workload is continuous and thermal management is the limiting factor. This case study forces us to reevaluate our hardware selection criteria. It suggests that investing in software stack optimization, such as Linux native tools and low overhead serialization, is just as critical as choosing the right silicon. A well-tuned environment on an efficient APU can outperform a throttled Windows desktop GPU for specific inference workloads because it respects the physical limits of the hardware rather than fighting against them. Understanding that more power often equals exponentially higher cooling costs and energy bills means we should look for systems where software and silicon are co-optimized for efficiency. The engineering takeaway is not to stop using powerful servers, but to recognize when a different approach yields better results per watt. When designing your next deployment, you must stop looking only at benchmark charts that ignore power and heat limits. Instead, look for systems where the OS, drivers, and application logic are tuned together to maximize throughput within thermal constraints. This is how we achieve high utility with significantly lower operational expenditure while maintaining reliable performance in production environments. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.